Okay, this is my last video in which we're going to use trig substitutions using our basic identities in order to accomplish a task here, which is usually simplifying an expression. But in this particular instance, we're just going to, as per the directions here, use a substitution that is given to us in order to write this expression instead as a function of theta, okay, or some function that we could determine the value of given some angle, okay. So in terms of the expression that we have here, we have this radical expression on the right. We say that this is the root of 4 plus x squared, but they're asking us to involve a substitution where instead of x, we're going to write in 2 tangent theta. So if we were to perform this substitution, this would become now 4 plus, now in here we would say 2 tangent of theta, and this was being squared. Now one thing I want to remind my audience is this: if you had the square root of a squared plus b squared, this does not equal a plus b. It just doesn't do it. I mean, that's just fundamental algebra. Now if you had the square root of a squared times b squared, well, that's the square root of a squared times the square root of b squared, and you could actually tell me that you would get ab assuming variables were positive. But the idea here is this: we can't just go ahead and take the root of both sides, but we can manipulate this. So in terms of what we know about rules of exponents here, well, first of all, 2 times the tangent of theta squared, if you had a product to a power, remember we can raise everything in this product to that power. So instead of 2 tan squared, we have now 2 squared tangent squared, which would give us a 4 tangent squared of theta. So what this allows us to do is, again, we can't just take the square root of these straight up, but what I can do is manipulate this. And by manipulate it, I essentially mean this. We say, well, I notice that both of these terms here and the sum have a common factor of 4. So I am going to factor out this 4, and I'm left with 1 plus the tangent squared of theta. Now, the reason why we can actually go ahead and evaluate things like this, not straight up right now, but in the near future here, is because this 1 plus tangent squared, again, in terms of trig substitutions, remember, whenever you see a squared trig function, you need to be thinking Pythagorean substitutions. Now, in terms of 1 plus tangent squared, according to Pythagorean identities here, we know that sine squared plus cosine squared is equal to 1, which allows us to build these other 2 trig identities down here. 1 plus cotangent squared is cosecant squared. Also, that tangent squared plus 1 is equal to the secant squared. But the idea here is this. I have down here a situation that involves a tangent squared and a 1. As a matter of fact, if we go back and look at this here, you'll notice that we have a tangent squared plus 1. It's just that instead of writing it tangent squared plus 1, we got 1 plus tangent squared. But I know that tangent squared plus 1 is the same thing as a secant squared. And the fact that that is a secant squared now allows us to rewrite this as instead 4 times, and instead of 1 plus tangent squared, we could say 4 times secant squared theta. So now that we have the square root of something times something, that is, the square root of, say, a squared times b squared, that would be a times b. We know the square root of 4. We know the square root of 4 to be 2. And the square root of secant squared would be the same thing as, and maybe I'll write this out here, we get the square root of 4 times the square root of secant squared of theta. But we say the square root of 4 is just 2, and the square root of something squared is just that thing, so we get 2 secant theta. So instead, we were able to use this trig substitution, x equals 2 tan theta, to write this expression, this 4 plus x squared, the root of that, as a function of theta. So this is some function of theta. Now we can say f of our angle is equal to 2 secant theta instead of 4 plus x squared. Cheers.